All right, so let's start our lecture today. So this is the second lecture we have in visual computing. And the topics today is face detection. So this is somehow like a continuation of our previous discussion. And a bit of recap what we discussed last week. So let's have a quick recap. Okay. So in face detection, we follow machine learning framework, so ML framework. Where we have training stage and testing stage. In the training, the input is data, in this case, image or images, plus their labels, that's right. And the output of this in the training stage is model parameters. For the testing stage, the input is a query image or test image, and also model parameters. So these two are exactly the same. We move from training to testing, and the output is the predicted label of the query image. Right, and especially in our discussion, we focus on an algorithm called Viola-Jones. Viola-Jones algorithm. This is not state of the art. The state of the art at the moment is deep learning based face detection. But Viola-Jones was very famous, was the state of the art before deep learning. Okay, so this is the most powerful non-deep learning that implemented in many different applications, including mobile phone at that time. Right, so in Viola-Jones algorithms, there are two basic components. Well, there are four actually, but the most basic components is number one is features. The features is called R-like features. R-like features. That is the first basic components that we have to know. The second component is ADA boost. ADA boost is a classification algorithm. So this is a classification algorithm. And this is a very basic components of Viola-Jones. There are two. It's two, R-like features and ADA boost. But to speed up the process, because Viola-Jones algorithm is a real-time algorithm, you know, when you take a picture of someone, the bounding box immediately appear on your camera, and that bounding box is the output of Viola-Jones algorithm. And when you take pictures of someone, you don't want to wait that long, right, to have the bounding box. So the bounding box of the face of the person has to be there immediately, instantly. And that is called real-time face detection. And for the purpose of real-time face detection, we need to have the third component. This is not really basic, but it's a fundamental in Viola-Jones algorithms because of the real-timeness, which is called integral image. So this is the third component. And the fourth component is cascading algorithms. So these two, integral image and cascading, are for the purpose of real timeness. If you don't want to have a real-time algorithms, we can have just 1 and 2 here, hard-like features and adapters. Okay, so this is the very basic component, and for hard-like features, for hard-like features, we learned there are 5 types of features, or 5 types of masks. Well, basically for the mask, we need to know 2D convolutions. And once you understand 2D convolutions operation, then you know what it means by features. So there are 3 types of masks, but in total there are 5 masks. So I just write here 5 masks. Okay. So I hope that you remember the mask, the 5 types of masks. And when we have these 5 types of masks, then we convolve this mask with the input image. And if we convolve this type mask with the input image, it can give you one mask, can give you 1 features. If you apply this mask many times, 10 times, then you have 10 features. And the collection of these features in terms of a factor, so you in the end of the day, these features in terms of the number have to be formed in a certain format, and the format is a vector. And from features, we will have descriptors. Descriptors is the other names of feature factors. Okay, so descriptors is actually a factor, feature factor. And we learned last week that we need to apply this mask for every single pixel whenever applicable. And the input image that we have, here in Phil-Jones algorithms, in the training process, it is 24 by 24 pixels. The resolution is very low, 24 by 24. And if we apply this convolution process of the 5 masks that we have on this 24 by 24 pixel image, then we will have a vector, a descriptor. And the length of this vector is, what is the length? 160K. So it's very long. So if you can imagine, feature 1, feature 2, feature 3, and so on until feature 160K. So that's the descriptors that we will have. If you don't remember the input image, I will show you how this input image look like. Let me see. Yeah, so this is the 24 by 24 input images. So one image, one face is 24 by 24. And then you apply this feature extraction here, type 1 and type 2 and type 3 in different scales, different location for all pixels, then you will have the 160K feature factors. So if you have 5,000 faces, if you have 5,000 positive samples, how many factors that you will have? It will be 5,000 factors. So one image will have 1 factor. 5,000 images, you will have 5,000 factors. Any questions so far? The things that you have to keep in mind is that the scaling up of the mask. That's a bit tricky. So you have to be able to imagine that, how the mask is scaling up for each of them. Scaling up, and then have to be done for every pixel whenever applicable. The basic idea is that the mask cannot exceed the 24 by 24 image. Okay, so it's always within this 24 by 24 pixels. So if you want to understand 160K features, then this is the algorithms. If you keep counting in these loops, then it will give you the counts, will give you 160K. So please try to understand these algorithms to give you the idea of how the mask is operated on the input image. Okay, so that's how we can get the feature factors. Any questions so far? Right. So if there's no questions, let's move on to this second component, which is the classification algorithm. Right. So we have other boost algorithms here. First, Adabus Adabus stands for what? Anyone knows what this Adabus stands for? Stands for adaptive boosting. Adaptive boosting. Boosting is one of the algorithms in. So this is boosting. Adabus is one type of boosting algorithms, and boosting algorithms is one of the techniques in classification. So this is part of classification. I'm not really sure how many of you taking pattern recognition, but in pattern recognition, I explained the basic task in machine learning. In machine learning, there are a few basic tasks. One is regression, and the other is classification. Of course, we have clustering, and of course, we have manifold learning. But most of the tasks actually fall into the first two categories. One is regression, and the other is classification. So boosting is one of the techniques in classification. So what this classification does? Classification is actually very straightforward. If you have a space, imagine a simple case of two-dimensional space, and you have positive samples. This is in the training stage. And you have negative samples. The main purpose or the main objective of classification is to find a plane, or in this case, a line, that separate this positive from the negative. So the line can be a straight line. In this case, it's linear classification. But the line can also non-linear. Okay, so there are two types of classification. One is linear classification, and the other is non-linear classification. Let's learn the simple one first, which is linear classification. So in linear classification, the task is to separate the positive and negative. And in the testing, whenever you have a point and you have features, and then your features in terms of the factors, you transform into this space. So for example, the query image fall into that location, the green point there, then you want to know what is the label of that green point, green sample. So in this case, if we know the red line, the classifier, then we know the label of that green point. Obviously, in this case, the green point is positive because this is above the line. And if it is below the line, it will be negative. So that's the whole point of classification. So in this case, we want to have boosting algorithms to separate positive, which is phase, and negative, which is non-phase. So you can imagine that the positive here, positive samples, is face image. And face image, you can look at here, for example, this one is face image, means that this is positive samples. All these are positive samples. Now, schematically, in terms of diagram, in terms of the pipeline, you have images, right? You have many images. And you want to input these images. I'm talking about training stage here. And once you have the images, the next things that you need to do is what? Anyone? If you have images and images here, the next step in our algorithm is what? Feature extraction, exactly. So we have feature extraction modules here. And what is the output of this feature extraction? Descriptors. How many descriptors that we will have? And descriptors. So we will have and descriptors. And once we have and descriptors, what will be the next step? What will be the next process? Anyone? What will be the next step? You will process these descriptors with classifier or classification. In this case, we use AdaBoost. And the classification module will give you some output or outputs here. What are the output of the classification in the training stage? Is the yes, the parameters. This is what we call model parameters. And in this case, the model parameters is called classifiers. Well, basically this red line here. The red lines there has parameters, right? A line has a parameters. A hyperplane or a plane has a parameters. If it is more than 2-dimensional space, it will become plane. If it is in 3D, if it is in 4 or 5 or 6 or maybe n dimensionality, then we will have hyperplane. And hyperplane has some parameters. And that's exactly the model parameters that we want to find. So if you don't understand what I say, then this line here, the red line in the space there, in simple case like this, how we can model the red line? How can we model the red line there? Y equals to mx plus b. Right? So in this case, m and b are the parameters that we want to find. So that's called model parameters. If we have the model parameters, then we can draw this line. In high dimensional space, again, if you cannot imagine what I just said, if it is 3D, for example, and then you have positive here and negative there, then you cannot draw a line. A line will not separate the two classes. You need to have a plane. And a plane is actually have some parameters, right? In a plane, in general, we can write ax plus by plus cz plus d equals to 0. In this case, if you write in the same way, in the implicit equation for the line, you can have ax plus by plus c equal to 0. So the higher the dimensionality you have, the more parameters you will get to separate the two classes. And again, here A, B, C, D are model parameters. Okay, so that's something that we want to find, right? Just remember that we want to find positive and negative. There are a few things there. So for these n images, here, what these n images consist of in training stage? What this n consists of? Anyone? Sorry? Exactly, phase and non-phase, positive and negative. So we have positive samples and negative samples. So if you have positive and negative, then we can find the line. If we don't have the positive and the negative samples, it's impossible for us to get the lines. So we need to have these positive samples and negative samples, the data and the labels. So in Feller-Jones, the requirement is that at minimum, you need to have 5,000 positive samples and 5,000 negative samples. Okay. Any questions so far? Now, I draw here two-dimensional space and three-dimensional space to give you the example of positive and negative, how they occupy the space. But in reality, how many dimensionality that we will have? What is the dimensionality of the space that we are dealing here? Anyone? What is the size of the dimensionality of the space that we have to deal with here? Yes? Anyone? I cannot hear. Can you speak louder? Exactly, 160K dimensionality. So the dimensionality that we are talking here is not just 2 or 3. It is 160K dimensionality. Well, I cannot draw this 100K dimensionality, let alone 160K. Even 4 dimensionality, I cannot draw. Right? So it's a huge space. Now that's one thing. Let's keep that in mind, that we are dealing with 160K dimensionality of space. And I think you will learn, I'm not sure if you learned this, but you will learn in machine learning or pattern recognition, the curse of dimensionality. There is a term like, because of the dimension is so huge, you cannot see them, you can analyze them, and that becomes curse. But anyway, so aside from this, let's imagine this positive, negative in a simple two-dimensional space. Positive and negative. And again, you want to find the line. In extreme case, as I mentioned, this line is not necessary to be a straight line. It can be a nonlinear line, curved lines. So now, positive, for example, have the restriction to occupy this space, right? And negative can be there, or maybe if it is nonlinear, in this case, it can be here as well. So in that case, you will have to find a line, something like that, to separate the positive and negative. Now, what is the best negative that you have to select? What is the negative samples in the first place? What is the negative samples in the first place? It's called non-phase, right? What is non-phase? What does it mean by non-phase? Non-phases. Non-phases implies anything in the world that are not phase, right? That's called non-phase. As simple as that. But then, what criteria, if you have to choose non-phase or negative samples, how you can choose non-negative samples? Will you choose anything randomly, like white wall here? What kind of negative samples that can be meaningful for your classification? So there are two types of negative, right? So because negative will affect your red line. So I can give you the example. If your negative is very far, right? Where will be your red line? Your red line perhaps here, right? Or this is the first case, the one case, and the second case is that your negative is close to your positive. Now, what happened with that? In that case, your red line will be closer to the positive. So which one is better? Case number one or case number two? Two, right? Obviously, because we want to constrain the positive, to constrain the boundaries, to constrain the classifier as close as much as possible to the positive samples. And this kind of mining, negative samples mining, is called hard negative. So we want to mine hard negative, because hard negative is more meaningful than easy negative. Okay, so there are negative here, there are two types of negative samples, easy negative and hard negative. As you can understand, that hard negative is better than easy negative. And that's require you to mine hard negative, which is called hard negative mining. Now, what is hard negative? What is hard negative sample? Can you give an example? Sorry again? Yeah, negative points is close to the positive samples. But in this case, in the phase recognition case, what is the negative sample? What is the negative phase? Hard negative phase. Sorry? Monkey face. Is that monkey face? Well, we do not know actually. Whether it's monkey face or it's something face, we don't know. But it's something that's close to face, but not face. So in that case, it's not easy because the definition of something is not face, but if something is face, something look like face but not face, it's difficult to find. So hard negative mining is hard. Right? Why hard negative is important? Because in the training, we don't want our boundary to be too loose. Because later on in the testing, non-negative is a lot. Non-negative is more than positive. So non-negative can come close to this space here. So that's why we want to find this one as much as possible to exclude this in the training. So the training has to be exposed to hard negative as much as possible, so that in the testing we are not trapped in the hard negative query samples. Okay? So that's why it is important. The hard negative is quite important in machine learning. Any questions so far? Okay, so that is the background of this pipeline, training pipeline. Okay, so let's now look at how we can get this line, right? Because finding this line is actually difficult. As I mentioned again, we are discussing about general classification, but now let's look at the idea of other boost or boosting in the first place. So the goal of boosting, to find a function that separates the positive and negative, right? To find a function that separates negative from the positive. And the basic idea is to have a strong classifier to find a strong classifier that is composed or consisting weak classifiers. So there are two terms here that's very important to understand boosting. One is a strong classifier, and the other is weak classifiers. So this is really the basic idea of boosting. Strong classifier and weak classifiers. So I can give you an example of what it means by strong and weak classifier. So let's assume that we use F1. F1 is the first features in your long factor, 160K factor. You just choose the first one, which is F1. So F1 is a one dimension, right? There is no two-dimensionality here. There's everything is one dimension. And the negative is here, for example, and positive is here. So the basic idea, of course, is try to find that line. In ideal case, if you can have that one, F1 can do the job already. You don't need to have F2, F3 until F1 is 60K. You can just use F1. But in reality, that's not the case. F1 is a weak features. F1 perhaps even not the part of the image. F1 is perhaps the corner at the image, which is non-phase. Right? So F1 is actually a weak features. So in reality, actually what happened is that the positive or the negative can be here, or even in the middle of the positive. So even in the middle of positive. I put it in the line because F1 is one dimension. We cannot draw it into dimension because it's just numbers, different numbers. So in this case, if you have to find a line, there are too many errors. There are a lot of errors if you force yourself to find a line. So the basic idea is that, okay, let's relax, not just use F1, but let's use F2. So the idea then, we use F1 and F2. If you use F1 and F2, if you consider F1 alone, it will be something like that. And then positive is here, and negative is there. So if you have F1 alone, for example, if you use F1 alone, this positive and negative will occupy the same space. So that's why you cannot separate them. Right? So this one also, that it will occupy the same space in F1 perspective. Now with F2, the idea is that we want to have this line and that line. Where the half of F2, now the dimensionality increases, then the possibility of separation will be there. Okay, so that's the basic idea of increasing your dimensionality. And in this case, this one is called the first classifier, and this one is the second classifier. So H1 and H2 are the weak classifiers. So H1 and H2 are the weak classifiers. And where is the strong classifier then? Is the combination of H1 and H2. So the combination of H1 and H2 is called a strong classifier. And that's really the basic idea of boosting. In three-dimensionality of space, for example, so we have F1, F2, F3, then you can solve more complex problem. So in this case, the positive is here, the negative is there, for example. If you have the perspective from this view angle, for example, if you put your eyes there, and if you look at this distribution of the positive and the negative, they are convolve each other. They are in the same, it seems to us, they are in the same space, in the same location, right? But actually in the higher dimensionality, you can have the opportunity to have a better separation. So in other words, the more dimensionality that you have, the more chance that you will be able to separate the positive and negative. Okay, so that's the basic idea of classification. Classification wants you to work in as much as possible dimensionality of the space. Because in that case, it will be, you will have a zero errors in the training process, because you will always have the hyperplane that separates the positive and negative. How complex your distributions, if the space is very high in terms of the dimensionality, more than the complexity of the data, you will always have the plane that separates the positive and negative. And that is the overfitting case in classification. So in classification, it will be overfitting if your dimensionality is too large. Because in that case, you will always be able to separate the positive and negative. Okay? So that is the case of overfitting in classification. Well, if you take pattern recognition, you will learn that actually. But we will not go deep in this course. Anyway, so any questions so far here? The main point here that you have to keep in mind is that boosting consists of two things: weak classifiers and a strong classifier. All right, so I give you another examples. So another example is this one. These are very complex distributions because the positive, the blue, is in the middle, and the negative, the red, are surrounding the blue ones. And as you can see here, there is a line here that is H1, weak classifier 1. And then you have H2, so this one, H2, is a weak classifier 2. And so on and so forth, until you have many lines that can, if you sum the line, if you combine the lines, then you will have much better separation between the red and the blue. So this one, all the lines in the very complex situation here are all weak classifiers. And if you combine them, as you can see in the picture, you can separate now the positive from the negative, the blue from the red. And this one showing the line here showing the energy function. So the more line you have, the less error that you will get. But then again, as I mentioned, you can be trapped in an overfitting situation. So you have to be careful. And in this case, you don't rely on the data alone, on the training data alone, but you have to use validation data. So in the validation data, hopefully there's some indication that there is a sweet spot, then you can stop. And the green curve here is called validation curve. Without validation curve, you do not know where to stop in this boosting algorithm. Any questions here? Any question, anyone? So boosting is always converge, but converge doesn't mean optimum. Okay, so when people say converge always optimum, that's wrong. Because in this case, it's converge, but it's not necessarily optimum. It can be overfitting. Okay, any questions? Right, so if there's no questions, now let's move on to other boost. Again, other boost means adaptive boosting. So the key words here is that differentiate it, other boost from boosting is adaptive. So what does it mean by adaptive here? So I can give you the example in the lecture note that I have prepared here. So this is what it is means by adaptive. So in the first stage here, number one, you have positive and negative samples. Then your algorithm decides that this is the most optimum one at that dimension. Means that, of course, there's errors, but the error is minimum compared to the other possibility of lines. So this line is assumed to be somehow optimum for one feature, for D1, for H1. It's still a weak classifier, but somehow optimum in a way, right? Or close to optimum, not just random. Now, in that case, then you have a rule that the left of the line is positive. The left of the line is positive, the right side all negative. That's your rule. And in that case, some samples, some positive sample, this one, will be wrong, will be in the wrong side. And for these wrong samples, you have to increase the weight. So adaptive here means there is weight for every single sample. In the beginning, the weights are all the same, uniform. But in the second stage, after you have the weak classifier, you put the weights more for wrongly classified samples. Okay, so that is called adaptive. And why is that the case? Because in the next stage, so here we put more weight on the wrongly classified samples. In the next stage, the classifier, the computation of the classifier can focus more on the wrongly classified samples. So in the next stage, this one becomes the focus. And in the next stage, we don't really care that much on that, but we care on this one. So in this case, the rule is very simple. The rule is for round 1 and round 2 and round 3 is very simple, that we just vertical line for the classification. So we always play with one dimensionality of features. We don't use 2 or 3 dimensionality. For each feature, we only have one straight line classifier. For this sample here, for this example here. So because we focus more on that, then our straight line, our vertical line will be in that location. Again, the rule is simple. The right is always negative, the left is always positive. Now, there will be some error as well, because this one now become errors, become wrongly classified, because that will be the location, the area of the positive, not the negative. So then we increase the weight of the wrongly classified samples. And by focusing on these wrongly classified samples, then we get H3, H4, and so on. Again, don't bother about the horizontal and the vertical. Later on, we will stick with the verticals, right? Just assume that vertical is more important. Any questions here? That's the basic idea of adaptive boosting. We put more weight to the wrongly classified sample so that in the next iteration, the classifier can focus more on these wrongly classified samples. Any questions so far? Okay, so if there's no questions, let's continue. So you know now the idea of adaptive. Adaptive means that we have weights to influence the classifier, the focus of the classifier. Now let's start with more difficult discussion. So you need to pay attention on this because this is really the heart of the Vela-Jones algorithms. So it's not intuitive that much anymore. So far we discussed very high level kind of topics, but now let's talk about the very detailed algorithms. So this one is Vela-Jones adapters. Right, so just want to remind everyone here about the input of our training system, training algorithms. What are the inputs? Anyone? What are our input? Sorry? How many of them? How many types of input? 2, right? What are those 2? Oh, too broad. We have to be specific now because we already learned about the pipeline. So we are here now. We are here. Right? In that case, what are the inputs? Descriptors. Descriptors and their labels. Okay, so we have descriptors and labels. So we have x1, y1, x2, y2, until xn, yn. And how big is n? What is this? N equals here? Yeah, n equals to, in our example, in our discussion, what is n? Almost. N equals to 10,000 because 5,000 plus 5,000 is 10,000. Means that we have in total n samples and can be split into 2, 5,000 positive, 5,000 negatives. So xi is descriptors, is one descriptor. Of sample I. And yi is what? Label. In this case, yi equals to either 0 or 1. This is negative. This is positive. Right, so this is the input. In the second step in the algorithm, we need to have initial decision, especially the initialization of the weight. So initialization of the weight. In other words, initialize weights. So the weight have 2 indexes. One is the index of the time, the iteration. In this case, versus initialization, the time here is 1. Okay, so 1 here is the time, is the iteration. You can put 0, but in the lecture note, I put 1 as the initialization of the time. And we have I. I is the index of the sample, the same as I here, the index of the sample. Right, so in this case, we have 1/2m and 1/2l. This is for positive and this is for the negative samples. Assuming m is the number of positive samples, and L is the number of negative samples. In our case, M and L are equal, which is 5,000. M equals to 5,000, L also equals to 5,000. Any questions here? Okay, so very simple initialization. The third step, so this is the iteration step. For T, again, T is time, the iteration step, the iteration count, 1 up to capital T. And the sub-step 1, we need to normalize the weight, normalize weights. And the normalization have to be done WT for every samples, for every iteration, for every samples, TI equals to WTI divided by the sum of a j equal to 1 until j equal to n, WTJ. So for every samples, you have to normalize basically with the sum of all the weights. In the end of the day, the sum of WT, 1 is always equals to 1. Okay, so we normalize the weight. Step number 2 is to select the best weak classifier. Select best classifier. So the equation for selecting the best weak classifier is epsilon T equals to minimum of all parameters. So theta is the parameters. Sum of all samples I, WT, I multiplied by H. H is the classifier. Xi, theta minus yi. Okay, so it's a bit cryptic. The equation is not really obvious in this case. But you can imagine, for example, when t equals to 1, right? So imagine that t equals to 1, because in the first iteration, t equals to 1 actually. And t equals to 1, it means that you implies this as F1, feature number 1. So you have long factors, F1, F2, F3, until F160K. F1 is the first number in your factor. Okay, so T1 implies F1. Please try to understand this, because if you get lost, you will not understand the whole algorithms. Okay, and because it's important, when I say important, it's important for your knowledge, but also important for your grade, because it will be in the final exam. Right, so please try to understand this. If you don't understand, please ask. Right, so what is the meaning of this, right? The meaning of this, we have to focus now on F1. So when we talk about F1, we can imagine there is a space here and F1 space. There is no y-axis. I draw the y-axis for the purpose of clarity, but in reality, there is no y-axis, only x-axis, because F1 is just one number with different values. Right, so you have positive here, maybe positive there. You also negative here, you have negative there. Okay, so that is the situation that you have. You have positive in one place, negative in the other place. So what it means by y1, yi is the labels that I just draw. The positive and negative are y1, yi. So this one is actually, you can say that this one is y1, y2, y3, y4, and so on. Okay, so that's the label of your samples. Right? So now what does it mean by this H? Again, in our previous discussion, HI or H1 in this case refers to the weak classifier. So let's assume that your weak classifier is here. This is H that you want to find. Okay. So that's H. Assume that you are given that H, which is H1 in this case. Now, what it means by H, a function of Xi? Oh, by the way, theta here refers to the parameters of H. So this one, H1, refers to theta, so a certain parameters. Means that in this line, it is, for example, H1 equals to 3, for example. In this case, this is 3. That value in the x-axis is actually 3. In that case, H1 equals to 3, right? And that one is actually the value of theta, theta equals to 3. So theta is the parameters of your line. Okay. Now we know theta, we know H, and what is Xi? So Xi refers to the sample. Hi is the definition of F1 basically. So in this case, X1 is this one, X2 is that one, in terms of the location in the F1 axis. Not the label, but in the F1 axis. So this one in X3, X4, and so on. So the location in the x-axis is called Xi for that sample. So let's take a look at this Xi. Xi is this guy there. Is this one. Well, it is not in the space, in the two-dimensional space, because as I mentioned again, we are talking about one dimensionality. So this one is actually, I'm talking about point there on the F1 axis. So in this case, as always, we have a rule for the line. The negative will be on the left. So this one, we have a rule that negative is the left and positive on the right of the line. So in this case, for this Xi, what will be the H of that Xi? Well, basically, this one is a predicted label. This one is the ground truth label. Okay. So in this case, what is the prediction of Xi? Is positive. And what is the ground truth? Yeah, what is Y? Yi in this case is also positive. Okay, so in that case, positive, remember, positive equals to 1. Here, positive equals to 1. So Xi is 1. Xi or Hxi is also 1. So 1 minus 1 equals to 0. That's if your samples happens to be Xi. If your sample is X3, if your sample is X3 there, right? If your sample is X3, what is your Yi? Y3 in this case. Y3 will be positive, which is 1. And what is the predicted value? Negative, which is 0. If it is 0 for your H and Yi is 1, then the error in this case will be 1 because there's absolute value there. Negative 1 absolute value is equals to 1. So in other words, if it is wrongly, if your sample is wrongly classified, it gives you higher number. If it is correctly classified, if every sample is correctly classified, the error, the epsilon will be 0. Epsilon will be 0 if everything is correctly classified. But the error will be very high if everything is wrong. Okay, so that's the meaning of this equation. In the first iteration, you don't need to bother about W because W are all the same. Any questions? Yes. Oh, sorry. Yeah, go ahead.
Why initialization you choose the W is equal to 1 divided 2?
So why this one is 1 divided by 2m? Yeah, so it's good questions. I do not know why this is 2m actually, but it's some divisional have to be there. I mean, it has to be made uniform basically. And in the end of the day, when you have ET, epsilon t have to go between 0 to 1. So W here, in the first iteration at least, because everything is uniform in this case, that have to make epsilon t between 0 to 1, cannot go beyond 1. So why this has to be 1 over 2m, perhaps to guarantee that it has to be smaller than 1. But there is no physical meaning on that. Don't worry about that. As long as the epsilon value is between 0 to 1, that will be fine. Yeah, a good question. Any other question? Yes.
So, for every t, we only focus on one feature.
That's correct. Yes. So every t, we focus on one feature. So the dimensionality of your space here is just 1. Right. So this is the genius of Taylor-Jones algorithms, because in this case, everything will be very simple. In one iteration, the operation is very simple. And that's the point actually, because it's a weak classifier. And that's exactly the meaning, the implication of weak classifier. We just focus on one dimension of the factors, of the features. Okay. Any other questions here? Yes.
So in that sense, the capital T where T ends is 160,000.
That's correct. So capital T, if you have to do it for all features, then capital T is 160K. But we will discuss this later on, how we can select the features. Yeah, any other questions? Good questions, that one. Any other questions? Right. So again, what is the meaning of this minimum with respect to theta? What does it mean by the minimum with respect to theta? What is the, in the first place, what is the meaning of this notation there? Parenthesis, theta under parenthesis. What does that imply? Again, if you take a recognition, you will know the meaning of that. This one is called the candidates. Candidates of the line, because theta implies the line, right? Theta equals to 1 means that the straight line crossing axis 1. If theta equal to 4, the axis value x-axis will be crossing at 0.5, and so on and so forth. So theta are the candidates for all the possible lines. So if your classifier is integer from 0 to 100, then the possibility there will be how many candidates that we will have? If you know theta have to be integer, and you have the range from 0 to 100, how many theta candidates that you will have? 100 lines, 100 possible theta. So in other words, you will have all the possibility there. And all these are the candidates. And the idea is that we have to choose one candidate that minimizes the error. That minimize the error means that the line has to be as correct as possible. It's not necessarily to be 0, but it has to be minimum. Okay, so ideally, we try to get a line when the majority of the left will be negative and the majority of the samples on the right will be positive. That will be ideal. But as you can imagine there, even if you just assume integer 0 to 100 of the range, you will have 100 candidates. Means that you have to try every single lines to see how many errors that you will have. It will be computationally expensive. And it is not necessary because once again, we are just trying to find weak classifier. We just try to find a weak classifier. It's a weak classifier anyway, right? So in this case, to speed up the process, we reduce the number of the candidates. So for example, we just choose 5 candidates. Now the question is how we can choose 5 candidates? Well, if you can know the distributions of the positive and negative, then it will be ideal, but that also takes time to compute the distribution of the positive and negative in your space. It's doable, but it takes time, right? So the easiest one is just random candidates. So you choose 5 random line. Of course, there's some, you should do it cleverly to select to find the positive random numbers. But that's the basic idea that we have, for example, 5 candidates, and these 5 candidates is chosen randomly, and then from these 5 you choose the best that minimize the function. Any questions here? Okay, so if there's no questions, I assume that you understand the meaning of this equation. So let's move on to next step, substep 3. So in substep 3, we define, it's not really a step actually, it's just a definition. HT is number 1, if we line number 1 in the picture number 1, of all x for all samples, so x bar in all samples, equals to h for all samples with theta t. And theta t is when your theta minimize the function. Theta t means implying epsilon t, the minimum one. In other words, this one is just definition that, you know, take this one for that one. So the orange line becomes HT, become your best classifier, best weak classifier. Any questions here? Again, the value of HTX there is either 0 or 1, because our label is 0 or 1. Anyway, so let's move on. And then the most important thing here is number 4, step number 4. This is the key of AdaBoost. We need to update the weight. We need to update the weights in such a way W t plus 1. So the next weight for of I equals to the current weight WTI multiplied by beta t power to 1 minus alpha I, where alpha I equals to 0 or 1, 0 if xi is correctly classified, and 1 else. So this is the important equations in adabus. So let's try to understand what's going on here. Let's see. So there is a definition of beta, but let's see what is the definition of beta first. Okay, so beta definition of beta here is beta t equals to epsilon t divided by 1 minus epsilon t. So if we draw this one, if we draw the value of beta, so we have a correlation between epsilon t and beta t. So again, epsilon is this one there, the quality of your classifier. Again, epsilon is the error of your classifier. It means the quality of your classifier. If your classifier is a bad classifier, means that too many errors, epsilon will be large or small? Large. And if your quality of your classifier is good, then epsilon will be 0 or close to 0. So let's assume that epsilon is 0. So 0 as the epsilon. In that case, beta will be, what the value of beta? If epsilon equal to 0, it will be 0. Now, if epsilon equal to 0.5, epsilon 0.5, remember that epsilon is from 0 to 1. The value of epsilon is from 0 to 1 because we normalize with the W. So if epsilon is 0.5, what is the meaning of that? What is the meaning of the quality in terms of the quality of your classifier? Well, it's not bad, it's not good, right? It's in the middle. So if there is 0.5, what is beta then? Beta equals to 1. Now, if epsilon equals to 1, which is very bad because it's the maximum number of error that you can get, what will be the value of beta? Infinity. So that will be the case up to infinity. Okay, so that's the graph in our mind about the correlation between beta and epsilon t. Right, so now we know about beta. Beta is somehow proportional to epsilon. So epsilon is large, then beta will be large. Epsilon is low, beta will be low. And that influences the values of your W for the next iteration. So there are a few cases here. So the first case is that alpha I equals to 1. Alpha I samples I equals to 1. It means what? What is the implication of this? It is correct or wrong? It is wrongly classified, incorrect classification. So sample I, xi, is wrongly classified. So incorrect classification. So for this incorrect classification, what will be the value of beta t? If this is incorrect classification, what will be the value of beta t? Anyone? Beta t to power of 1 point to alpha I. Sorry, so I make you confused. So if it is incorrect classification, then alpha I equals to 1 and beta t 1 minus alpha I equals to 1. So what is the implication of beta t equals to 1? W t plus 1 I equals to WTI. Means there is no change in your weight. If it is incorrectly classified, you keep the weight of that sample. Agree with this? Any questions? Okay, so that's one case. So now let's take a look at the second case when alpha I equals to 0. Alpha are equal to 0, it means correctly classified. Xi is correctly classified. And in this case, and for example, epsilon t is small. Again, epsilon t is small means it's a good classifier. So your weak classifier is a good classifier. And it is correctly classified. Your sample is correctly classified. In this case, Wt plus 1 for that samples become smaller or larger? Become smaller. Okay, so if it is correctly classified and your classification, your classifier is a good classifier, then W becomes, in the next iteration, becomes smaller. Any questions here? Yes.
How to make sure the weight classifier is good? You say that the candidates they choose the random.
Yeah.
How to make sure the epsilon t, but the beta t is smaller than 1?
Well, we do not know. It's really up to the system. What will be the value of that epsilon? If the value of the minimum value of the epsilon is 0.6, for example, and that's the best one from all the 5 random candidates, then we take that as 0.6, and then in that case, epsilon is not small, but rather large because it's beyond 0.5. Right? If it's beyond 0.5, beta will be greater than 1. If beta greater than 1, if there's beta greater than 1, then it's always increase the weight. So when I say that it is epsilon t is small, it means that beta t is smaller than 1. So here it's the definition of when the definition of epsilon t to be small is that beta t have to be smaller than 1. That's the definition of epsilon is small. Good questions. Yeah, I forgot to mention that actually. Okay, so whenever beta t smaller than 1, that is the definition of epsilon t equals is actually small, which is a good classifier. Any other questions here? So let's take a look at the third case. Alpha I equal to 0, correct classification, and epsilon t is not small, it's large. Means that beta t greater than 1. So that up there, beta t greater than 1 means that epsilon t is greater than 0.5. And that's the definition of bad classifier. Okay. So in this case, what is the implication on Wt plus 1 on that samples? It becomes larger. Right, so that is the mechanism here. If it is incorrect classification, you keep the weight. Means that in the next iteration, don't too much focus on this. Well, you have to focus, but not that much. But if it is correct and the error is low, means it's a good classifier, beta t less than 1, then you tell the classifier, don't bother about this. don't put attention on that because it's already correct, right? But then for the third one, it's actually correct classification. But the error is high. It's a bad classifier. And in that case, you increase the weights. Why is that? Why is that? Why we have to increase the classifier for case 3? Increase the weight for case 3. Well, it means that you don't trust the system. You don't trust your classifier because you think that the classifier is a bad classifier. Even if it is correct labeling, correct classification, you have to penalize that. I don't want you to be mean, but in daily life, the analogy will be, you have someone very nice to you, always talk sweet to you, right? But in the back, he or she talk rubbish on you, right? You'll feel to be stuck on your behind. So in that case, you will penalize this person more than someone that look like nasty, but it's really not that nasty to you. Right? So that's the analogy here, to have these 3 cases mathematically. All right. Okay, so any questions so far? So this is what you do in the training process. In the training process, you keep this ideally for all the features, 160K features. And as the output of this, then you have H1, H2, H3 until H160K. And not only that you have H, not only that you have the classifiers, the big classifier for every features, but you also know the quality of these classifiers through epsilon. Through the epsilon, you know how good the quality of your H. Now, if you are the designer of these algorithms, we don't want to have T equal to 1 until 160K, because that will be too long, right? Then how do you choose the best T? How can you choose the best T? What will be the ideal case? This one is in training. In training, you can do forever, is fine. But in the testing, you have to choose, right? Which classifier that you have to take, because you cannot verify for every single features in the testing, because testing needs to be real time. So in the testing, which classifiers that you have to choose? The best one, the good one. You don't want to have bad classifiers in your testing stage. So how to choose the best one, how to choose the good ones is through the error. So epsilon T is very important. So as much as possible, you want to find the best epsilon, the epsilon that is small, and ignore the one that is too high, because that will be useless anyway. You cannot trust them anyway. Any questions here? Yes.
Does it matter if you pick the order of?
Yeah, a good question. Whether the order of the features matters here or not. Any question? Any answer for this? Whether the order of the features in the iteration matters? No. Yes, the answer is no. But you have to be consistent, because we do not know which one is good anyway in the beginning. So if you want to start from F1 and F160K, it's fine. If you want to start from 160K backward, is also fine. If you want to take random, it's also fine. But it has to be well. Random means that you have to keep the order. Right? You have to remember the order of the random sampling. Okay. Any other questions here? Yes. Sorry again, I cannot hear you.
Will the later classifiers be better, like the ones which are evaluated later?
I see. Right. Because the order doesn't really matter. It actually doesn't really matter which order. This is a bit different from my previous. That's a good question. Because maybe you get stuck with this description here or depiction here. This is a bit different from Vela-Jones adapose, because Vela-Jones adapose doing the computation of the classifier one by one. It doesn't really matter the order because it's independent from one feature to another feature. The computation is totally, well, not totally independent because you have the adaptive weights, but as long as you have what I want to say here, as long as you can have that set of features. So, for example, the best one is 1, 3, 1, 2, 3, 5, 7, 11, which is prime numbers, right? Assume that the prime numbers are the best features. Then you take that prime numbers and train based on these prime numbers. Train your algorithms here. Train your algorithms here based on the prime numbers selected features. In that case, you keep the process of the adaptive weights, because this process of adaptive weights is important for your testing. Does it make sense? Okay, good. Any other questions? That's a good question, yes. Any other questions? Okay, if there is no other questions, that's all for the process of this Vela-Jones adapose. Now, what we get from this training process is weak classifiers. You can choose 100, 200, 300, depending on the capacity of your computers, because again, this is offline. This is training process. You know, you can take your time to do the training process. It doesn't really have any constraint on the time, computational time. But after we get the weak classifier, again, the idea of boosting is to form a strong classifier based on the weak classifiers. So how we can form a strong classifier? So a strong classifier is not part of the training process. A strong classifier is only useful for you in the testing. So that's why the strong classifier is actually used in the testing. Okay. So what is the definition of strong classifier? Strong classifier. So a strong classifier, if you have C, is called C is a strong classifier function, and C have an input of X, a sample, but this sample is not the sample from the training data, but sample in the test data, which is query data. So in this case, X is test. So X here, sorry, not bar, but X test. X is a vectors. This is a vector with length of 160K. Okay, so X is a descriptor of 24 by 24 image. And the strong classifier will classify whether this X test is either 0 or 1. It is phase or not phase. 0 is not phase. 1 is phase. It is phase if the sum of T1 until capital T. Again, this one, if you want to use all the features, it's okay, but of course it will be slow. or you can just select, for example, the prime numbers that I just mentioned, right? So T here, selected features. And this one depends on gamma T multiplied by HT X dash greater than or equals to 1/2 T equals to 1 up to T gamma T. And 0 non-phase if it is else. Okay, so this is a bit complex equations. So this one is a bit complex equation. So let's try to understand what's going on there. So for simplicity, forget about gamma. Okay, so for simplicity, forget about gamma. In that case, you will have phase if T equals to 1 until T HT X dash greater than 1/2. Well, gamma T here equals to 1, for example, then it is half multiplied by anyone? T, capital T. So what does it mean by this? So let's try to understand this part first. X dash is 160K features, and HT is your weak classifier. So remember that if it is just T equals to 1, for example, when T equals to 1, H1 dash, H1 X dash. So what does it mean by this H1 X dash? Is that you have, again, this one is F1 or T1, right? And you have a line here that already H1. So you have a line already decided by your system to be the best at that features. Okay. So in this case, you can have H1 already. Remember that the left is negative and the right is positive. That's the rule that we impose. And X dash actually have F1 dash. Right? The first value of the vectors for X dash is equal to F1 dash. And assume that F1 dash is here. That's the location of your F1 dash. And in this case, what would be the value of H1? Is equals to 1 because it's positive. F1 here is considered to be positive by H1. So the output of this equals to 1. If your X or F1 dash on the left, then it will be labeled as negative or 0. Okay. So now, if this one here, this term there, the green terms, equals to T, what does it imply? If I say to you, okay, so sum of this equation equal to T. All the classifiers classify your test data, your test samples to be positive, to be 1. Means that all the classifier, the weak classifier, agree that that one is a positive sample. This is very strong. Means that it's very, very confident. Okay. So what happens if it is 1/2? It means half of the classifiers consider that your sample is positive, and the other half think that it's negative. And that is the rule that we want to impose there. That's the rule that we want to impose here. What does it mean by that? What is the meaning of that equation then? At least your classifiers, your weak classifiers say that this is phase. That's the least. Half of your classifiers should agree that it's phase. Otherwise, it is non-phase. If it is less than half, then it's not considered to be phase. Any questions here? It's very straightforward, right? Okay, so now let's get back into the blue one, the blue box. The blue box say that, well, okay, half of them have to be positive, but now we also depend ourselves on gamma t. So what is gamma t? So gamma t equals to log 1 over beta t. If you use beta t definition of epsilon t 1 minus epsilon t, for example, then you can have a derivation that log 1 over epsilon t divided by epsilon t, right? I can write in that way. It means that I can have log 1 over epsilon t minus 1. And if I have this correlation, I can draw the correlation here. So the correlation is between epsilon t and beta t, and sorry, gamma t. If epsilon t equal to 0, what is gamma t then? Epsilon t is 0. It will be infinity positive or infinity negative? Positive. So it's very large here, right? So if epsilon t is actually 0.5, for example, what will be the value of gamma t? It will be 0. So it will be something like this. If epsilon t equals to 1, then what happened? Yeah, it's negative infinity. So it will be something like that. So that's the correlation between epsilon t and gamma t. So we know that epsilon t represents the quality of your classifier. If epsilon t is 0.5, it's in the middle, not bad, not good. But if it is less than 0.5, it is considered to be good classifier. So this one is a good classifier, and that one is bad classifier. So we know now here is if epsilon t is positive, then it's good classifier. If epsilon t is negative, then it is bad classifier. So that implies what we have here in the blue box. The blue box, if epsilon t is positive and really positive, means that it's very large, then it will have a lot of influence on your HT because it's multiplied by a large number, positive large number. But if your epsilon or your quality of your classifier is bad, then your gamma t will be negative, will not be contributing that much into this decision. If it is 0, if it is 50-50, it doesn't contribute that much. So that classifier that have 50-50 in terms of the quality will not be considered in the decision in the test stage. Okay, so again, here HT is not uniform. We have some weights as well in your weight classifier. The good weight classifiers will take important role, more role than bad classifier. Okay. Again, the easiest one is to assume that the classifier is 0, is 50-50. Means that that one will not be considered at all in this computation, in the strong classifier. And if it's negative, essentially it's degrading the consideration. It's likely that it will be, if it is full of negative, you will never achieve that the left side will be greater than the right side if everything is negative. So, but you can design this by not considering the negative, not considering the 0.5 above kind of classification of V classifier. You can remove that V classifier in the start actually, and you just consider 50-50 kind of classifier and better classifier in your design. So don't bother about the bad classifier to be included in the strong classifier. So for the strong classifier, choose the best and the good weak classifiers. Okay, any questions? Yes.
Would the performance be better if I discard all the bad classifiers?
Yeah, that's what I just said. Yes.
Why should we just keep those classifiers that have epsilon greater than 0.5?
We keep them. Yes, we keep them. That the epsilon that has the classifier that have the epsilon greater than 0.5, we keep that. And that one, because that one is a good classifier, we can rely on them.
I mean the bad classifiers, just discard them or just...
Yes, you have to discard them. You don't use in the strong classifier, because in the strong classifier here, actually you can choose which one that you want to use. It's not necessarily you have to use all of them. So T here, T equals to 1 until T. You don't do it naively. You don't do it for every features. You just choose the one that is good features. Yeah. Any other questions here? Yes.
So we train the feature after we estimate the frequency of T, or we just choose the feature before that.
Yeah, so there is that's a good question. There's a mechanism here that you need to be careful because the adaptive of the weights influence the strong classification in the end. So the best way is try to first find the best features independent from each other. Okay, so you can have for each of them, you can somehow have a rough idea which one is better than the others. If you compute independently, you know, if you put in you compute independently without the weights, just compute each of these features, you somehow know which features are better than the other features, right? And you use that features, select some of them, and then you start training this based on this iteration.
At the start, we have choose all of the features.
That's correct. So as I mentioned again, you select, for example, assume that the prime numbers features are the best, are the good one. So choose this one first. Choose the prime numbers first, and then use these prime numbers in this iteration. Okay. Yeah. Good questions. Any other questions here? Yeah.
Simply after we discard all those bad classifiers, we only have gamma T that is positive.
That's right. So hopefully we have a gamma T that is positive. Yeah, because that's the positive gamma that is more meaningful in our classification of the phase detection. Yes.
But to discard all the bad classifiers, would the capital T still be 160?
No, it will be much less.
Use another notation.
Yeah, we can, but this one, there is no definition that this one have to be features. I mean, not necessarily have to be 160K features. So in the paper, actually, they choose 200, around 200 features to be selected in this process. Yeah. Yes.
During the iteration process, I think that because when T equals to in this iteration, we get the fast weight classifier and we adapt the weight. But in the P plus 1 iteration, will it be meaningful for the next iteration? Because we just get this fast weight classifier in this iteration. Will it be meaningful for the next iteration? Because there are different feature states.
Sorry, I cannot. Can you rephrase again? Can you say it again?
Because there are in this iteration of feature, we get according to this iteration of T, we adapt the weight, right?
Yeah.
It is we adapt the weight in this iteration. When we get to the next iteration, I wonder if it is meaningful.
What do you mean by meaningful?
Because features are independent.
Features are independent. Yeah, but again, even though they're independent, we want the next classifier to focus on the wrong one. Because in the end of the day, we will combine them. So in the end of the day, in the strong classifier, we have to combine them in the same process. Right? Because we have to combine them in the end, then, for example, if I have 1 and 2, so assume that capital T equals to 2, right? So in that case, the first one will give you wrong classified samples. And in the iteration, in the training process, there is a mechanism that the second classifier will focus on the wrongly classified one. Right? So for that mechanism that we need to somehow do the adaptation of the weights, because in the training process, that's the key idea of adaptive boosting. Because in the second stage, in the second step, we need to focus on that wrongly classified. So then the classifier can focus on that wrongly classified samples.
Although it is although the feature are
The features are independent, but the connection in this training process for finding the best classifiers based on the weight. Yes, yes. So that's why I'm telling you that assume that the prime numbers are the best classifier. Then you need to train that prime number sequence in this iteration. So then you can have the correlation in the training process, the correlation between different features. Yeah, I understand that's a bit difficult to intuitively understand that, but yeah, that's a good question. Yes. But it takes some time for you to think about this and at home, for example, and reflect how it works. Yeah.
But if we focus more on the samples instead of the features, would it be possible that if we do not?
We don't really. I don't understand your statement there that we focus on samples, not features, because the features here is actually the space. The space is actually based on the features. We do the classification based on the features.
I mean, just like what he said, if we, if we do not modify the weights, would it be possible that in the next iteration for the next feature, the result would be better if we do not modify the weights?
Well, that's not other boost. That will be boosting, right? If now the question is whether boosting is better than other boost, right? That's a good question. I do not know whether other boost is better than boosting, but in general, people know that other boost is better than boosting in terms of the, at least in the, of the experiments, right? So now in theory, what is the advantage of this other boost? In theory, it's because the next classifier can focus more on the wrongly classified. If it is not focused on the wrongly classified, the convergence here will be very slow. It will not be as drastic as that one. It may be more or less flat. And that's a little bit a problem in terms of the learning process. Because you can, in other words, your learning process is not fast enough. And that's the problem of boosting compared to other boosts. But that's a good question. In theory, how we can prove that other boost is better than boosting, I do not know at the moment. But maybe if you find the articles, comparing other boost and boosting, maybe there's some explanation on that. Yeah, good questions. Any other questions?
So the difficult application.
Yeah.
So after we selecting the features that we use during the training process, we don't change them between.
We don't change. We don't change because, as I mentioned again, the sequence of the prime numbers have to be kept. If you think the prime numbers features are the best features. Yeah. Any other questions? Okay, so if there is no questions, let's have a break. So we start the second session 10 minutes past 8. Is that fair enough? Yeah, 10 minutes past 8. Yeah.
I want to ask you, always said, like this one, we want to put more attention to the points that we misclassify, right? But after we said, even though it is right classified, we still largely attention, but the wrong classified point we simply change the weight. So is that just different from
Well, the logic is the same, right? So the wrongly classified one is bigger.
But this we always maintain the
Yeah, but the correct one, number 2, is smaller.
But this is only to the frequency.
Yeah.
Smaller
So the correct one is keep smaller, right?
Yeah.
The correct one is smaller now.
Yeah.
The wrong one is the same, but it means that we still pay.
Attention is different.
Well, don't bother about number 3 first. Okay, so forget number 3. Consider number 1 and number 2. Number 1 and number 2 means that the wrongly classified one bigger than the correct one, right?
Yeah.
That's the same as what I explained in the beginning, right? Now, you understand that, right? It's correct, right? Number 1 and number 2 is correct. So number 3 is something that we don't trust. It is correct, but we don't trust the system because it's the classifier is actually bad classifier. So that's why we penalize even more.
Correct point.
Not to trust, but it is, you don't trust the classifier basically. If you don't trust classifier, you penalize so that the next classifier can pay more attention on it.
But you don't trust it just because it corrected the correct classifier just.
No, not little point, by accident, by chance, because the classifier is wrong. It's very wrong. The classifier is quality of the classifier is bad.
It's bad because like we have 2 points. It just corrected by 2 points.
No. So yeah, so that's right. The error is high. The error for the classifier is high, but it happens for your sample for your particular photo I, it is correct. But it's not always for all other samples. So we don't trust this bad classifier. If you don't trust, then you have to ask the next classifier to take a role, to take more role. Because you don't trust it. You don't understand. My suggestion is take your time, think about this first, and then if you don't understand, you can come back. It's yeah, take some time. It's not necessarily have to be offline, it's a bit online. Yeah. Oh, yeah. So as I mentioned again, in the initial process, in the mechanic, in the procedures, you have to, in the beginning, you have to choose the good classifier. Yeah, they are good enough. Independently, they are good enough. Yeah. Yeah.
One sample classifier itself is that. Then we will interest.
Yeah, we analyze. Yes, we ask the next classifier to pick one of that.
The next classifier.
Performance.
So you can take a look at that formulation, the equation. So for example, the weight of that sample is increased. Then
The next classifier will pay attention on that because the weight of that particular sample is high.
yeah, but the weight of the rest samples are low.
Yeah, so
Compared to
yes, compared to that one. Okay, so if the classifier, the error will depend on the weight of the classifier. So if it's still wrong, then it will penalize more.
So it's possible that for example, that correct sample that has a weight of one, the rest of the has some weight like very close to zero.
So
Then
my suggestion is here. My suggestion is that think about this first, right? And think in the ways. If you still have questions, you can come back to this. But at least you have to think first because it's complex and maybe you can find the answer after you think sometimes. And then you can, of course, you can come back to me next week. Yeah.
So this picture.
So it's a good classifier. To be considered to be good big classifier. Yes. So as I mentioned again, in the beginning, beyond the algorithms, so it's not stated in the algorithms, but it's separate from the algorithms, that you have to choose somehow good classifiers independently for each feature. You can, from independently, you can say something, right? You can, this is good or bad, right? It's bad because it will be high. So choose this one first. Initially, you have somehow good classifier, for example, 200 of them. So in this case, P, capital P will equal to. So originally you have 160K features. So your T is actually 160K. But you don't do that. First, you have to find independently good classifiers. No, not through this. As I mentioned, beyond this algorithm, it's not mentioned in this algorithm. So you can choose independently by independent features. Independent features is actually independent, right? You don't really do the iteration, but independent for each feature. So in that case, you already know somehow good features, roughly. Well, if it is epsilon is greater than 0.5, it will be good, right? Smaller than 0.5.
Yeah, epsilon is a indication of the quality of the classifier. Yeah, but not including the weights. The weight has to be removed. So that's the first process that I didn't mention in the algorithm. So you have to choose that one without W. Yeah, so you choose one. Yes, in this one. Yeah. P is the iteration, the study.
So that's
The index of the classifier.
index. So that's all the prediction label for.
No, not classifier is the line. The line here with the positive and negative. So for each feature.
So in this age, as HSI, that means with the classifier we set it on 50.
Yeah. So H here is the value is 0 or 1.
Yeah. Okay. So it means in every step, T is from 0 to 2. So that's the every.
T equal to 100.
Yeah. So that means the for every step.
Every classifier in the every features.
In every.
Oh, okay. Yeah. So, well, you can just really ask someone there or just mention it. Don't worry about
I want to ask what should I show for next week?
yeah, you can
have any specification or you can just get some code from the
yeah.
and try to run the
So I suggest that you talk with Jiahao. So just call Jiahao whether what is the expectation that you just so one by two, right? Then you have 1 by 2 is you multiply by 3, 3 by 6, and 1 by 2, 3 by 6. So you're confused about the combination. It's not really important. As long as it is, of course, we cannot in the middle of the pixels. So you just choose whether you have to draw the right or the left. Yeah, don't worry about it. It's not really important. As long as you keep the depth the same. Yeah, in ideal case, if you don't bother about computational time,
then you can have a lot of thousand iterations. Yeah, so if you want to speed up, you don't want to process all 160K, but many of them are actually meaningless. Then you have to choose. So now how we can choose? For example, if you choose 200, D equals to 1 and 200, but not in the sequence of features, but you just choose 200 features. So in that case, you have to find, before the algorithm, you have to find two features. And once you can know the two features, independently find the features that is less than 0. The epsilon value is less than 0. Then choose 200 of them, then this is the if you want to speed up the planning process. So number one and number two can show you. Number one is it is formula, then it's the same, but it is correct. Small. Don't put them together. Yeah, number one is correct, but it's still the same. But it is correct. Then it is small. Yeah, one hand, but the logic is the same, right? Because number two is smaller. Yeah, number two is smaller. Yeah. Yeah, it's
right, so let's start our second session. I thought a bit on the questions, which one is better, other boost or boosting, right? That was actually a good question. So I thought a bit, and maybe the answer is because of negative hard mining, negative samples, hard negative samples mining. So what does it mean by that? In other boosts, when you wrongly classify it, and then you have to focus on that, it means that that samples is actually hard samples. Because in the first place, you wrongly classified that one. So that one is hard samples. And the idea of other boosts is to ask the next iteration to focus more on hard negative samples. And that will be more powerful because in the beginning, we discussed about hard negative mining, right? So that's something that I have in mind. Whether this is true or not, please clarify. Just Google whether other boosts, what is the comparison between other boosts and boosting. Okay, right. So next, we discussed already about the classification. Right, with this classification in our mind, then we can start doing testing because that's the whole process of training, right? So now let's discuss the testing algorithms. So the testing here have some input, right? What is the input of this? In the testing, what will be the input? A strong classifier, that's correct, a strong classifier. And what else? Yeah, query image or test image. And what is the test image that you have here? What kind of test image is that? What is the test image look like? Face, yes. What is the resolution? Yeah, 24 by 24 image. 24 by 24 pixels image. Right. And the output will be, what will be the output? Right, so this is predicted label, and this is 0 or 1, which is the output of your strong classifiers, a strong classifier. Well, actually, yeah, I cannot say that it's a strong classifier. It's better to say weak classifiers, which is implies strong classifier. Okay, so in this case, in the testing, if you have to develop the algorithm for the testing stage, number one is what? What will be the process in the algorithms in the first step? Given the input image, so this one is a grayscale. Remember, this is grayscale. Given the input image of grayscale 24 by 24, then the first step is to extract features. Extract feature or extract descriptors. Compute the descriptors. And secondly, what will be the second step? Yes, use the strong classifier or predict the label. So is this something that we want? Remember in the beginning, we set the goal, right? What was the goal? Is it something that already achieved the goal? What was the goal? I can remind you, this is the goal, right? That's the goal. Given that kind of image. Is it the same as the input image you have? No. Your input image is only 24 by 24, a single image. This one is arbitrary image. You do not know the scale, you do not know the location. So our testing here is actually very naive because the input is very simple, 24 by 24 image. And this is not something that we want. So we have to develop a better testing algorithm. So in the proper testing algorithms, what will be the input? What will be the input here? Any image, any grayscale image. Any here means any size. All right, so if your input is any image of any size, what will be your algorithms? Number one, if you are the programmer, how you can solve the problem? You need to crop the image, crop the window, crop the patch, right? So we need to crop starting from 24 by 24 pixels for every location or for every pixels. For every pixel, you have to crop 24 by 24. Because 24 by 24 is the minimum. And it's quite small actually. 24 is very small in terms of the image. And that's enough for starting point. You crop, and then second thing is use strong classifier, apply strong classifier. And then you can see whether this 24 by 24 crop patch is face or not face. Agree with this? But it's not sufficient, right? Because the size of the image is unknown. It can be larger, most likely to be larger than 24 by 24. So the step number 3 is to increase the size of the patch or the window. Increase the size of the windows that you crop. Maybe 30 by 30. Maybe by 30 by 30 this time. And also scan for the whole pixels. For every pixels. Now, because your patch 34 by 34, you need to downscale it. Downscale to 24 by 24. And then apply this strong classifier. You iterate this one by increasing the size further and further, and downscale again to 24 by 24, and so on and so forth. In theory, you can solve the problem using this algorithm. But what is the problem? What is the problem with this algorithm? Anyone? What is the problem here? It is, yes, what is the keyword here? It is very slow. It is very slow. If you have to have this algorithm in your mobile phone, you will take forever to get the bounding box on the face. Right? So it's not applicable in any applications. And this is a real problem. right? If you want to make it applicable to real application, we have to solve this because this is testing stage. It's not training. In training, you can take your time, but in testing, you have to be real time. So this one is actually naive algorithms. And to solve this problem, there are two ideas. I mentioned this already in the beginning. One is to use integral image. The integral image will solve the sub-window generation. So the window, the cropping is a problem, right? Cropping and downscaling problem. So integral image will solve the cropping and the downsampling problem, and also the scanning, cropping, scanning, and downsampling. So integral image will solve all this. And the other problem here, which is not really written in the algorithms, but you know, in the strong classifier, even though you already choose the best one, even though here you already choose the best one, for example, the best one is 200 classifiers, but you have to go through all these 200 for every single patch. So for every single crop that you have to apply 200 kind of evaluations based on the weight classifiers. And most of the time, if you look at your picture, if you take a picture of me here, what happened actually in the reality? The number of faces are much smaller than the number of non-faces. So in other words, the number of faces are actually sparse in the input image. In other words, it's likely to be 1 or 0 if you are given the crop images. It is 0 or 1. It is likely to be 0. So we have to be conservative because the fact that the faces are rare, not rare but sparse. Okay, so for that reason, we will see later on that has something to do with cascading. The basic idea of cascading is that if the first features already say no, already say that this is not face, reject them immediately, not waiting until 200 features. That's why we have to be conservative in that way. Okay, so that will speed up the process as well. Any questions here about the high level ideas and motivation? Yes.
You mentioned that we in the crop and downsampling, we just downsample every 30 pixels to 24 and 24, and for all the larger size. So can we just downsampling once, like downsampling the full picture and then use it for the scan again?
Oh yes, you can. You can downscale the image, but then the problem is it will be the same, right? Because you do not know how much that you have to downscale the image. You can downscale the image many times, for example, 10 or 7 times, but downscaling the image is also takes some time. So, for example, if you have an input image 1000 by 1000, right? You downscale it into 700 by 700, you downscale 500 to 500, and then you downscale it up to 100 by 100, for example. And then you have to do the operation for every pixels for all these images. Still very slow, right? Yeah. Of course, the naive idea of the algorithm not necessarily in this way. Any possible variants are also okay, but doesn't solve the problem of the computational problem here. All the possible algorithms still have this slow process. And that's actually the point. The point is that if you don't use integral image, your algorithm is likely to be slow. Yeah, any other questions before we move on the technical discussion? Okay, so if there's no questions, let's start with this integral image. Okay, so the next topic will be integral image. So the integral image formulation is that I, x, y. So maybe for efficiency, I guess I can just copy and paste. Right, so this is the formulation for integral image. Right, so, well, it is a bit cryptic, the equation, so let's take a look an example here. So let's assume that we have input image. So input image here is I refers to input image. So I is simple 2 by 2 image. Let's have 5, 3, 2, 6. And the index here is from 0, 1, 0, 1. And the goal is from this I, from this input image, we want to compute II. II is integral image. So this one also have 2 by 2. The index is the same, 0, 1, 0, 1. So let's take a look for these numbers here. What would be the number there, right? And in 0, 0 location, what would be the value for the integral image? So let's see. So II 0, 0. II 0, 0 equals to what then? II for the according to the formulation, I 0, 0 equals to I minus 1, y is 0. And this one, plus S 0, 0, correct? And S 0, 0, S 0 minus 1 plus I 0, 0. So what is I 0, 0? 5, right? What is S 0 minus 1? 0. What is S 0, 0? 5. And what is I minus 0 is 0. So this one becomes 5. So you do this for all the location. In the end, you will get 8 here and 7 there. And this one will be 16. All right, so that's the definition, the understanding, the example of integral image formulation. Any questions here? So that's number one, the formulation. No question, I think, right? It's very straightforward. It's mechanical. I mean, just follow the formulation, then you will be fine. Number two is the concept of computing a block or block computation. So block computation, you can imagine that you have blocks. So these blocks So one cell can be 1 pixel, can be multiple pixels. So one block here, one block here is not necessary to be 1 pixel. It can be 1 pixel or more. Okay, that's called block. Let's assume that this one is II. You already have integral image computed from your input image. And for every single node here represents your block. So you have block A, block B, block C, and block D. And you also have node 1, node 2, node 3, and node 4. So node 1 equals to A. A again is value. If it is 1 pixel, then it's 1 value. So in this case, A, for the example that we have here, A equals to 5. If your node is here, if your node is there, for example, this node number 1, your node number 1 equals to 5. But if your node 1 is in that location, then it equals to 16. Okay, so that's the meaning of that node. In this case, if it is one cell, then 1 equals to A. So let's assume in this case, for simplicity, that A, B, C are just 1 pixel in the integral image. So 2 equals to, the node 2 equals to A plus B. Node 3 equal to A plus C. Node 4 equals to A plus B plus C plus D. So this is called block computation. All right. Now, the questions here, given the value of 1, 2, 3, 4, what is the value of D? You are given the value of 1, 2, 3, 4, then you can ask yourself, what is the value of D? In this case, by definition, you can have D equals to 4 minus D equals to 4 minus A plus B plus C. And A plus B equals to what? A plus B equals to 2. 2 plus C. And C equals to what? 4 minus 2 plus 3 minus A. And then what is A? 1. 4 minus 2 plus 3 minus 1 equals to 4 plus 1 minus 2 plus 3. So that's how you compute D if you know 1, 2, 3, 4. Well, it's very simple elementary school exercise, right? So now why this is useful? I'll give you an example why this is useful. So forget about this because this is just very mechanical. Okay, so now why this is useful? Let's take a look at the example here. So you have input image I, and it happens that you have 4 by 4 image. And the value here is 5252 5353 636 252 636. So this is your input image pixel values. And if you compute the integral image according to the formulation, you will have 5. What will be the next year? 7. Next after that, 12. Next after that, 14. Down here, 8. Down further, 13. Down further, 16. And yeah, this is a bit difficult to compute. 16, I think, and then 24, 32, 23, 32, 36, 46, 48, 64. Okay, so don't worry about this because computer can do it very, very quickly. Right? Because it's very mechanical, very following the algorithm, the formulation. So now why this is useful? Again, that's the questions. So the basic thing is that remember in hard features, hard-like features, you have to do block computation as well. Because you have to sum positive conform with positive 1 conform with your pixel value, and then you sum them, right? And in the negative 1 is the same. You negative 1 multiply the pixel value, and then you sum them to get the features. Right? So that's a block operation basically. And that one, for example, if all these, let's just simple case for all these, for example, right? That is your convolution with positive 1. If that's a convolution with positive 1, then you have to sum this, right? Sum these pixel values. So what is the sum of these pixel values here? Anyone? It is 16. For this computation, how many numbers that you have to include? How many numbers of numbers that you have to use? How many numbers of numerical value that you have to involve in the computation is 4. If I increase or upscale the mask, then there is a possibility that I will have that as a mask, right? Because I increase the scale of the features of the mask. In that case, if you have to compute this block, you have to sum all of them. How many numbers that involved here? Is 9. If you increase further, then will be more numbers that you have to sum. And that's a problem, right? So we want to simplify this additional or the summing operation. We want to simplify the sum operation here, not depending on the number of the values that we have. So how do we do that? Let's take a look here. So let's look at the red block. Red blocks means that we want to find dot here, node number 1, node number 2, node number 3, node number 4. Remember that we want to find node number 4, because node number 4 is the sum of A, B, C, D. Remember, this is node number 4 is the sum of A, B, C, D. And A, B, C, D here is actually the ABCD. So in this case, D red equals to 4 plus 1 minus 4 here is a node numbers plus 3. Yeah, according to this equation here. That's block D. And this one 4 is what? 64. And 1 here is 16. Minus 2 is 32. Plus 3 is what? 32. Equals to what? 16. How many numbers that you involve in the computation? 4 numbers. If you use integral image, it is only 4 numbers. That's for the red here, for the red block there. Let's look at the green block, D green. D green, now D greens, we have here block number 1, here block number 1, here block number 3, here block number 2, and that block number 4. Okay. So again, number 4, block number 4, node number 4 equals to what? Equals to 64 plus block number 1, which is 5, minus 14 plus 16 equals to what? 39. So what is the number here? The sum of this green block? 6 plus 3 plus 6, 15, 17, 23. Well, you can compute yourself, but I believe this will be 39. So if you use integral image, the computation is much simpler and faster, because you only need to have four numbers all the time, regardless the size of your block. So the big O, if you know big O, computational big O notation, so big O here equals to 4, constant 4. The other one is linear, the same as the input numbers. So that's the magic of the integral image, because it can reduce the computational of the masking. When the convolution to get the features now is much faster. Any questions for this integral image? Okay, so if there's no questions, let's move on. Testing stage. Oh, by the way, this integral image can be used in the testing, can be used also in the training. Well, in the training it's not critical, but in the testing it's very critical. Because in the testing we want to be real time. So the input is the same. The input is any image. Input any image with any size of image. And the algorithms. So first is what? Compute the integral image. That's the first step. The second step, generate blocks or generate windows starting from 24 by 24 for all parts of integral image. So basically the same here, 24 by 24 for the whole image, for the whole integral image. And then you just compute the descriptors as per normal. Well, you have to consider that this is an integral image now, so you have to use block operation. Okay, so the block operation has to be used. No, because we are no longer using image, input image, but use integral image. Number 4, Okay, so that's 24 by 24 for the whole block in the integral image. Then we have to increase the mask, right? Now, increasing the mask here, imagine that you have integral image now. So you have to imagine the integral image. So if you want to increase the size of the mask, what you need to do is to increase the block size. In the beginning is 24 by 24. Now it's up to you. If it is increasing here, means that you increase the mask by any factors. In the paper is, I think, if I'm not wrong, is 1.7 times. I'm not really sure why 1.7 times based on the experiments, I suppose. 1 point something, I don't really remember the second digit, but it's either 1.3 or 1.7, I'm not really sure. Please check in the paper, in the Philadelphia paper. So you increase the mass, means that you increase the block here. So it is not 24 by 24, but if it is multiplied by 2, sorry. When I say that the 1.7 is not multiplication of that one. It is not the multiplication of 24 by 24, but the multiplication of your mass. Remember that if it is 24 by 24, the standard mass is 1 by 2 for the first mass. The second mass is 2 by 1, right? That will be the standard mask for 24 by 24. But then you have to increase the mass, right? So the increasing the mass means also that in that 24 by 24, you have to increase the block by multiplying them with 2 for the mass. Is that understandable? That you have to start with 24 by 24, and in this 24 by 24, you have to handle all different scale of your mass. And that has to be done in the step number 2 here. Step number 2, still doing the 24 by 24. Now, 24 by 24 is assumed to be the face size. But in your real input image, it's likely that the size of the face will be larger. Right? So now, if it is larger, in the previous algorithms, you have to increase the 24 by 24 cropping. Right? But in this case, we don't need to do that. We don't need to increase the crop. What you need to do is to increase the starting point of your mass. Remember, if it is 24 by 24, one of the mass has to be 1 by 2. Right? But now, if you want to increase the resolution of your face, then you have to increase the first mass that you have. No longer 1 by 2, but multiply that with a 1 by 7, 1.7. That will be your starting point of your mass, starting size of your mass. In that case, you don't need to increase the resolution of your patch, but you increase the resolution of your mask. So in that case, it will be more efficient because we don't really need to increase the patch, don't scale it into 24 by 24 anymore. Okay? Because now every block operation can be done more efficiently using block operation. Is that understandable? Any questions on this? Any questions, anyone? Yeah, think about this at home and try to understand what's going on there. Yes. Yeah.
What makes window starting from
because the 24 by 24 is the smallest size of the face that we want to anticipate.
So assuming image with 36 by 36
26, 24 by 24, you mean.
36 by 36.
36 by 36 is what?
I just don't understand that what means all part of the
So remember that we have this input image, right? You have to imagine that your input image is like this. It's not 24 by 24. You convert this into integral image. We do not know how it looks like. It's basically just numbers, right? So 24 by 24, assume that your face is 24 by 24. Of course, it's wrong in this case, but we start with something. And if you assume that your face is 24 by 24, you will start with 1 by 2 mask, right? And 2 by 1 mask. And then you increase the mask many times, so you can have 160K features for this 24 by 24. You have to do that as well. But then there's no face there. Your classifier says there's no face there. And then you increase that, right? Normally what you do is you increase the patch. You increase the patch. That's what your naive idea that you have to do, right? When in the previous algorithm, the naive algorithms ask you to increase the mask, increase the patch. But using integral image, you don't need to do this explicitly. Instead of increasing the patch, you increase the original first mask size. The original first mask size is 1 by 2 if it is 24 by 24. But if it is, say, 37 by 37, for example, then you start with not 1 by 2, but 1 by 7, 1.7 multiplied by 3.2, for example. You start with that as the first mask, and then you increase the mask from there on. Is that understandable? In that case, you will have higher resolution of the patch. Basically the same effect like this one. But still you have to scan this because that one is there's no face there. You have to scan for that face, for that size. So the scanning is still there. The scanning is still there, right? But the scanning, the computation of this is very fast. And not that fast, but you know, the complexity is constant for every operation. All right. Yes.
So the size of the last will be integer, so it will be.
Yes, it's not integer. It's not considered integer. Of course, in the integral image, you have to make it integer because otherwise it is not possible to be half of the cell, right? So in the discrete integral image, you have to round it up, round it down. Yes. Any other questions? Yeah, if you want to have a larger resolution of the face, then you have to start with larger mask. Yes. Larger mask, how like feature mask. Any other questions? Okay, so the last one, I assume you understand this. So the last one is very simple. As I mentioned, cascading, right? Cascading is very simple. So what happened with cascading is like this one. This is the cascade of classifier. As I mentioned again, so if your block, you don't need to compute all the features. You can just use your good features. Start with your good features. Okay, so you don't need to have 160K anymore. Choose one that is good. For example, 200. All right. If it is 200, it is good features, and then the first feature already say no. Then you have to reject that. This is what I said as a to be conservative. And then if this yes, your first feature is say yes, then you move to the second features, second classifier. Any of them say no, then you have to reject. This is very conservative algorithm. But the purpose is to make it faster because human face is sparse in the image. And this makes everything very fast because you just use good features, one mask, and check whether this is bad or good. If this is good, it is bad, reject immediately, move to the next samples, move to the next pixels. So the movement of the scan is very fast because it's just one feature that you need to select most of the time. If it is immediately rejected, that will be one feature. So the movement of scanning the pixels is very, very fast because of this cascading. Right, any questions? Yes.
I still don't understand how about this complicated image. I don't understand why you can have like 160K to 200.
Oh, that one. So, right. So, in the training stage here, right? We discussed previously 1 until T. T here, if you don't have any problem with the number of features, then it will be 160K, right? But we know that it's not necessary to be 160K because most of the time, if you look at the image here, so 24 by 24, the first feature 1 by 2 is blank, non-phase region. So many of this is non-phase region, right? So in that case, it's definitely, you know, the most corner of the image is useless. Actually, 1 by 2, most of them are useless. So useless means what? Useless means that the error epsilon t is very large, likely to be large. So if you look at the algorithms here, epsilon t is likely to be large, means that most of the time they are useless. So we know that if the feature independently verified, you don't really need to do this iteration, but independently apply this for every features without weight. You ignore the weight because the weight is unknown. For every features you apply these algorithms, apply this equation, you will know epsilon t independently. And some of them very bad because it doesn't represent any features of the base. So you can remove them. So in the end, in the paper at least, they mention that they use only 200 something features instead of 160,000 features. So from this independent verification of epsilon t, we can have a much smaller number of features. In this case, for example, 200 features. So when you apply this training process, capital T is not necessarily 160K. It can be just 200, selected 200. Not the first 200, but selected 200. So in my example, when I answer the question, this 200 is like assumed prime numbers of the features. Of course, it's not prime numbers. It's just an example, so that you can know that it is not sequence, but some selected features. So that one is used here in this training. Right. Any other questions? Again, the second session, we focus on integral image and cascading. And using the integral image and cascading, the process of rejecting and accepting whether a patch is a phase or not will be much, much faster. All right, any questions before we end the lecture today? Okay, so if there's no questions, that's all today. Thank you, everyone, and I will see you again next week. Thank you.
We use larger mask. Then this is the combination of the peptides.
It's okay.